Good afternoon. It is 1:30 p.m. in Philadelphia. Welcome to Thermal Live 2016. I'm Graham Kilshaw with Electronics Cooling Magazine, and this presentation is Utilizing Thermoelectric Devices to Optimize Thermal Management Systems. I'm joined this afternoon by Chris Kaler, who is the Technical Director for Phononic, the presenter of this afternoon's session. Chris is located in North Carolina in the fine city of Durham. And for this presentation, Chris is joined by his colleagues, Abhishek Yadav, Jesse Edwards, and Alex Gashard. Welcome, gentlemen.
Thank you, Graham, and welcome to all the registered attendees and those who are listening to us live and that might be listening to this after this live presentation. We appreciate your interest in the use of thermoelectrics for thermal management, and we are going to structure this as a roundtable discussion where we'll be very interactive with questions and answers, and we definitely are looking forward to answering direct questions from the audience, most likely at the end of the session. So I'll jump right in, and I'm going to ask Alex to describe for us and for the audience the general way that thermoelectric devices work, and that will get us started off to how we might use them in systems.
Sure, yeah. Hello, everyone. Thermoelectric devices are, in essence, solid-state semiconductor-based heat pumps. They consist of substrates, we call them headers, on either side that act as your heat exchange surfaces, and on the inner side of the device are patterned metal traces to act as current carrying elements. The thermoelectric elements are a semiconductor-based material that in the direction of charge flow also creates a temperature gradient and heat flow. So that thermoelectric device, as you apply current, the top gets cold and allows you to pump heat to the other side of the device. So you can think of those individual thermoelectric elements as a group being connected electrically in series, but thermally in parallel. And in the end, they're heat pumps, so they can convert electrical work to thermal work and heat flow, and vice versa, in the case of energy gen applications.
All right. Well, so as you said, the devices themselves convert electrical energy to thermal work, and so that sounds a lot like a compressor or just a heat pump in general. So Jesse, how do thermoelectric devices differ from typical vapor compression cycles?
Well, fundamentally, both vapor compression systems and thermoelectric systems strive to pump heat from one volume to another. The biggest differentiator between the two is a thermoelectric device, while, as Alex mentioned, is fully reversible thermodynamically, it's also reversible both electrically and thermally, which means that by reversing the polarity of the heat flow, you can reverse the functionality of the heat exchange system. So it's a fully reversible system, but at the same time, it's a self-contained and variable capacity system, which most compressors do not offer. There are some variable capacity systems, but in general, the variable capacity capability of the thermoelectric systems enables them to do jobs that are very, very difficult for other applications. Also, vapor compression systems have as a requirement for the function of transporting heat the need for an evaporator and a condenser, an expansion device, and a nice pumped circuit, which allows it to be remotely located, which is typically a problem. But the secondary heat transport, that pumped circuit, is a different animal with respect to a solid-state system. The thermoelectric elements operate to move heat independently of any other systems being attached to it. By enabling that secondary heat transport mechanism efficiently, the systems can operate at a very high performance level as long as the parasitics are taken into account and the DTs are minimized, because as the capacity drops, the efficiency of these devices goes very high, although it is peaky.
Jesse, there at the end, you mentioned efficiency, and I think all of us that have worked in thermoelectric devices and materials for a long time know that that's one of the first questions that we're always asked is what is the efficiency of a thermoelectric device? So, Abhishek, how efficient can thermoelectric devices be, and how does their efficiency dictate how they are used?
Yes. So thermoelectric devices are heat pumps like we talked about in previous two slides, and efficiency is denoted by the standard COP, coefficient of performance terminology for heat pumps. So the COP for any heat pump, whether thermoelectric or compressor based, will scale inversely with delta T. So if you get a higher delta T, it will be lower, and a lower delta T will be higher. Thermoelectric devices show very good COP at low delta Ts. Generally, they should be applied up to 40 to 50 degree of delta T, and after that, their efficiency will drop. And multi-stage devices or other kind of refrigeration methods should be looked at. And the other thing to note about the efficiency is that it is highly dependent on the current, as is shown on the graph on the lower right. So you want to operate them at the peak efficiency, and you want to design it such that your operational load happens at the peak efficiency. So that is very key to a good thermoelectric system.
Mm-hmm. And so, Jesse, back to you. It sounds like that the way a thermoelectric device would operate and how efficiently it would operate would depend a lot on other parts of the system outside of the actual device. So when you take into account a full thermal system, including electrical controls, firmware for controlling the device, that's where you can make the thermoelectric system the most effective. How should people that are listening approach system designs when they're using thermoelectrics?
So fundamentally, the classic disconnect with thermoelectric systems is a capacity versus an efficiency. And in order to deliver the correct capacity for a specific application, you would historically have to give up efficiency in that application. So it's very important to understand that while thermoelectrics are perceived as being inefficient, in actuality, when they're used properly and applied properly to the actual solution needed, they can be very efficient at a system level as long as you do not burden them with additional parasitics, fans, pumps, things like that to move the heat. As long as that's done effectively, a thermoelectric refrigerator can be just as effective and just as efficient as a vapor compression-based refrigeration system.
Mm-hmm. So, just expand on that a little bit in terms of what are the subsystems that designers should think about when they're designing with thermoelectric devices?
Probably the most overlooked is the thermal interface. So that is the actual contact between what your heat exchange mechanism is and the actual device itself. With relation to how those devices move heat from one place to the other and what's required to do that. What is key is that the best thermoelectric devices or the best controls or the best transport systems are ineffective in and of themselves to create a system-level architecture that's competitive with vapor compression solutions. It requires all of those working in harmony with each other and taking into account all of the parasitics, all of the losses with respect to not just the thermodynamic system itself, but how that system is controlled to confirm that it is operating within the band, the targeted COP band, while being still able to provide all of the capacity needed for that system and to eliminate heat leak back, particularly in refrigeration applications, when the system is de-energized.
And so, looking at that chart that we have up right now, when you said the parasitic losses, what we're talking about there, you mentioned the importance of interfaces too, that the delta T's between, say in this case, the heat accept system and the heat pump, and then again the reject delta T to the heat reject system, those are what the parasitic losses that can be really detrimental to a thermoelectric system that most people may have neglected in the past, but that's why you say you have to look at it as a whole system.
Yes, historically the heat transport systems used with thermoelectrics are extruded aluminum heat sink systems. And the fin effectiveness and the overall efficiencies of those devices drive the DTs on both sides of the device, either up or down, depending on the functionality, which pushes the thermoelectric device into an unfavorable COP condition. By eliminating the losses as much as is practical on the interfaces and through the heat exchange systems, you're able to bring down the device level DTs as compared to the system level DTs so that they're more in favor of operation. And that typically means that your reject temperatures are barely supraambient and your accept temperatures are barely under your target temperature range. That can be difficult, but it is certainly accomplishable. And in so doing, with a properly designed thermoelectric system, you can provide efficiencies or energy consumptions that are directly equivalent to a traditional, typical vapor compression solution.
All right, thanks, Jesse. Alex, we've said a couple times now here about interfaces. And of course, we just talked about how reducing the thermal resistances or the parasitic losses on the actual accept and reject systems. But how should we think about interface resistance and how that plays a role in how the system works?
Sure. So in any thermal system, whether thermoelectrics are utilized or not, thermal interfaces between components are very, very important. You can look at the different solutions for providing that interface, be it a thermal paste or thermal interface material like a grease, or even solder. Also conductive epoxies. All of those behave under the same physics. And to minimize thermal resistance, you want to minimize variability in that interface. You want to minimize voiding, and you want to minimize the bond line. And so when designing with thermoelectrics, it does become very important, especially due to the high heat flux that thermoelectrics are capable of, to design that interface properly. So the dispense pattern of whatever interface material you're using, the amount of compression applied to achieve desirable bond line thicknesses, and even things like thermal budget when you're working with a solder, those can be engineered to make sure that you are not running into thermal budget issues with the next higher assembly or with the component itself. So in the end, at Phononic, we take that interface very seriously and actually use automated equipment to define and process that interface. And we often will go back and check our work with characterization tools to inspect buried interfaces that are between two pieces of metal or between the ceramic device and a metal heat exchanger plate.
Mm-hmm. Thanks, Alex. It's really an important part for people to understand how the critical interfaces can add sometimes more thermal resistance to the whole system than the actual heat exchangers themselves.
That's right. A lot of people like to think of those as ideal interfaces, and that's not always the case in practice.
But one thing I'm just going to revisit on the last slide is that we talked about the different mechanical components of the system, the accept systems and the reject systems and the heat pump itself. But one of the things that can be real critical in the efficiency of a thermoelectric system, before we jump into more application stuff here in a few minutes, is the electrical control system. Jesse, revisit for us again real quickly how people should think about, Abhishek mentioned the current as being a very important parameter in terms of where do you run, and that we saw how the COP curve peaked at a certain current. Give us again some useful information for the engineers listening, how they might think about controlling a thermoelectric system.
This ties in very well to the concept of variable capacity. So as the voltage or current or power input changes, the capacity and the efficiencies change with respect to that. If you do not control that effectively, you can have a system that is very, very efficient thermodynamically, but very poorly controlled and regulated. What that means is the devices themselves act as essentially a resistor. And if you were to PWM a bucked voltage rail to reduce capacity for the system, what you end up doing is basically delivering a full voltage signal to the device, and it will act and behave as if it is at that rail voltage, and the PWMing is simply bleeding efficiency out of your system. So it's important to drive these appropriately, best with a direct DC outputted signal. And that allows you to more dynamically control the capacity, as well as make sure that you are not inadvertently running the system outside of its design envelope simply because the way you provide power to the system.
Right, so it sounds like the bottom line there for our listeners is some typical control mechanisms where you just turn on and off, which both with pulse width modulation, PWM, turning on and off a high voltage means you're running the thermoelectric at a low efficiency point, whereas running it maybe more on time, but at a lower current, let's say, allows for a more efficient operation of the device. So I hope that's given us a good introduction to thermoelectric devices and how they're being used. And of course, we'll be following up with questions at the end of this session, and even further down, don't feel free to contact any of us at Phononic for more details on those things. I'd like to use some of our time here to use some case studies of specific applications. Of course, we look at thermoelectrics being used in many markets, as you can see on the screen. And the first one, Abhishek, I'm going to ask you to comment on that. For temperature control, we talked a lot about refrigeration today, but for temperature control, thermoelectrics have been used quite a bit in the datacom and telecom markets. So describe the job they do for these applications for our listeners.
Yeah, so they are widely used in datacom and telecom, and the main benefit they bring is the control of the emission wavelength of the laser. So the laser wavelength will vary with temperature, and having a thermoelectric cooler allows you to control the temperature of the laser and allows you to control the wavelength. And this is very useful for DWDM applications where where even a little bit of drift in wavelength cannot be tolerated. So they are widely used, but these are very precision devices, and precision integration methods have to be used to make these packages. Generally, in these cases, the techs are mounted in a co-bar package, as is shown in the lower picture. Then the laser is mounted directly on the tech, or sometimes a carrier base plate can be used to mount the diode on the base plate and then mount the base plate on the tech. Thermistor is used to control the temperature, and the light is coupled to the fiber, so there's a lensed fiber. You can also have other components to manipulate the light, like lenses and mirrors sitting on the tech. So all of these components. So this because this is very precise assembly. Additional design parameters which should be considered here is the deflection due to thermal expansion, which can cause the lasers to go out of alignment from the fiber. Also, finally, as in all thermal systems, the heat sink and the interface resistances have to be carefully used in the design.
So in some ways, this is a very straightforward system in that there's a thermistor, in this case, that you see on the slide that's measuring the temperature. The thermoelectric can be used in heating or cooling mode to bring the laser to the same temperature in as large ambient conditions as possible. Yes. So in this case, it's for stability of the temperature, and it can be. Just want to make sure I point out for the listeners that one of the nice benefits of thermoelectric devices are they can be used in opposite polarities to heat and to cool, and with good efficiencies for heating, and sometimes even better than that for cooling. So I just want to make sure we point that out for the listeners. Moving on, Alex, beyond fiber optic applications, we want to go into how else can they be used for electronics cooling. Can you describe one application that would be near and dear to most people, which is how we can cool their processors in their computer.
Absolutely. So, in general, for cooling microelectronics and in particular CPUs inside of PCs and servers, the solutions that are out there currently do a fairly good job of cooling processors, especially given ever decreasing power requirements of home kind of commercial chips that are available. However, they're very large. You could high-end, high-performance air coolers and all-in-one liquid loop coolers designed for PC cases tend to be very large and take up a lot of space. So this particular cooler is called the Hex 2.0, and it's thermoelectrically enhanced such that in low power consumption modes and low power dissipation modes by the CPU, where say the CPU is at idle or under very low taxation, this cooler acts just like a normal air cooler, and that's enabled by the what we call the active-passive design, where the thermoelectric devices are simply not needed. That allows us to minimize power consumption and avoid the risk of condensation near critical electrical components. And that goes back to what we've already discussed about electronic control and making sure you're controlling properly for the application in mind. It's also, larger coolers can be high performance, but they can also be very loud. This particular version we designed with quiet in mind, and it's actually silent below our measurement capability at our nearby anechoic chamber at low fan speed. And it's high performance. Our goal was high performance with a small form factor, and this is comparable to those larger high performance air and water coolers that are twice or three times its size. And it's compatible with the TDP ranges of processors that are available today.
So it sounds like, I think the take-home message for our listeners, especially the engineers and designers, is when you design a thermoelectric system, you don't always necessarily have to size the thermoelectric part to take the heat load of the entire system. You'll see this in a lot of the systems that we design, this active-passive mindset where you can allow part of the heatsink to act, without power, without the thermoelectric device, and then the thermoelectric device and that part of the heatsink can be used as a safety net, or in some cases to make sure that in extreme environments that the device will survive, but you won't need to use that power at all times and in all environments. So that, I think I just want to make sure that that's one thing that comes across. So this is a good example of a situation where you don't need to use the power all the time when the CPU is at idle or under very low stress, and it can come on only when needed.
That's right. And just briefly building on that, you can think of it, typical passive and forced air systems, you need to design and size it for even the most extreme applications, whereas here thermoelectric devices are providing a space-saving and size reduction capability, because you can start with a small cooler to work passively and as forced air only in that lower power consumption mode, and then utilize the thermoelectric devices in high power mode, and you net save cooler volume for the application.
Mm-hmm. And speaking in the next application, speaking of extreme environments, one of the things that we wanted to bring to the attention of our listeners today was the application of outdoor TVs and displays. It seems like we're seeing more and more of those in the marketing or information kiosks. And so, Jesse, can thermoelectric systems bring advantages to this kind of application over other cooling technologies?
Well, yes, absolutely. Primarily, their form factor can be very advantageous because alternative cooling technologies obviously take up volume. But by using the active-passive logic As we all know, outside is not one temperature. It gets hot, it gets cold. It allows the system to dynamically react to the conditions so that, as Alex mentioned earlier, when we get into a situation of extreme environmental conditions, the system can compensate for that and ensure that the system, the device, the display, what have you that it's integrated into, is still able to maintain optimal functionality. And this is without burdening that system with something that requires 100% duty cycle or 100% active cooling, when that's simply not necessary for the primary portion of the operating life of these systems. However, everybody wants to get their slushy from the drive-through when it's 100 degrees outside. The display doesn't like that, and it needs to have the ability to dissipate that heat. And the options are to put large heat sinks on these and burden them with external volumes, or to integrate something like a active passive cooling scheme to enable them to be compact form factors without affecting their ability to survive in extreme conditions in both heating and cooling.
And I want to point that out. We talked about extreme conditions. We're usually thinking about a hot, sunny day in Dubai, right? But it also could be a very cold winter's evening in Bozeman, Montana that we're dealing with. So heating and cooling, both important in those cases. So it seems that there's a straightforward comparison between thermoelectric heat pumps and the compressors, as we kind of started with. And I want to wrap us up here before we started on the Q&A time to really talk about how thermoelectric systems can actually compete with compressors in the most basic of applications, and that's refrigeration. So Jesse, please enlighten us some more on how can refrigeration really be done with thermoelectrics in a way that's compatible with or better than compression-based systems?
So the biggest function of the refrigeration is the performance of the system. As performance requirements increase with respect to laboratory, scientific, or medical applications, the temperature uniformity within that chamber and the stability of that chamber becomes a critical factor to the acceptable performance levels. We've all had frozen celery and spoiled milk in our refrigerators because the energy requirements for residential refrigeration cause the uniformity within that chamber to be poor, which allows for large temperature differentials. In the medical space, that's not acceptable, and because of that, vapor compression systems have to work differently in order to be able to provide the stability and the uniformity required for those applications. But because the thermoelectric devices are variable capacity and they are continuously operational, they don't have to cycle on and off in order to provide cooling or heating for the application. They're able to provide precision temperature control really as a side effect of the way they operate. And that allows for a given performance level of temperature stability, uniformity capabilities versus a vapor compression solution to provide not only better temperature regulation and temperature control, but lower energy consumption to do the exact same job. So it's very important to understand that as the problem statement is presented, the solution should be most applicable to the application. We use vapor compression solutions historically because that's what was available, and not because it might be the best solution for a particular application. That doesn't mean that a residential application isn't effective, but it goes to the problem statement. How do you define what the performance levels are, and how do you pull out energy? Because it translates almost directly. Higher performance requires more energy. How do you put the system together with respect to the controls, the heat pump itself, the heat transport? How do you put those together into a system that at the end of the day from the wall power is comparable to or better than vapor compression while providing better reliability, smaller form factors, larger internal volumes versus external spaces, as well as reduced energy consumption?
Thanks. Thanks, Jesse. And thanks. Before we jump into the questions, I just want to leave 1 minute for, I think, a question that we get asked quite often, which is about the use of thermoelectric devices for power generation from a temperature gradient instead of trying to maintain temperature or cool it. So, Abhishek, tell us a little bit about what we're seeing with power generation and what kind of applications might be gaining some notoriety in that kind of realm.
Yeah, so variables have been gaining a lot of traction in the past few years, and they're generally low-power devices, and where thermoelectric devices come into play is that they can be used for power generation to generate the small amounts of power which the variable might run on. So they can actually be used where you would not need any kind of charging. The main challenge in application of thermoelectric devices here is the form factor flexibility. So you have to make both the heat sink and the thermoelectric device mesh well with the form factor of your wrist or wherever you want to put it. And that is a big challenge which the industry is trying to address right now.
All right. At this point, I'd like to turn the moderation over to MP Devakar, who's a senior tech editor at Electronics Cooling. And so he's going to help us to answer some of the questions that have already been posted by the audience today.
Okay, thank you. Thank you, Chris, and the Phononics team. Good presentation. I enjoyed it. We have quite a few questions, so we'll try to answer as many as we can. We have a hard stop because, as you know, the Thermal Live continues on at 2:20. We have another presentation starting. So let's get to it. The first question from Kshitija from ASU. That's my alma mater too, Arizona State University. What she's asking is, can we cascade these devices, thermoelectric coolers?
Yeah, this is Chris. I can take that first one. So, yeah, cascading of devices have been used quite often in the past, whether it be the physical cascading of actually separate devices or the building up of multi-tiered devices. So this has been seen most often in focal plane arrays or other kinds of very temperature-sensitive IR detectors where they need very low temperatures for detectivity to be better. So yeah, and that allows. So what happens when you cascade these devices is you can build up the delta T's based on the multiple delta T's across each tier or each cascaded level. So you can get to much larger delta T's than you normally could from a single device. The penalty that you pay when you do that is efficiency. So as you can imagine, the power that goes into each level to get the delta T and pump some heat is transferred to the one below it. So every device down the cascade has more heat to pump and more electrical heat to pump from each stage above. So typically you'll see efficiencies drop, but you get a much larger delta T available to you, get to much lower temperatures.
Okay. The next question from Gary, he's wanting to know the application of thermal grease, and does it leak, ooze out after compression? I think this is more of a practical, I would say, manufacturing or fabrication question.
Sure. Yeah. Part of that is this is Alex Gashard taking that one. Part of that is proper grease selection at the beginning. There are several different suppliers, and I'm not going to plug any particular one here, but there are several different suppliers that use solvent-based greases where the solvent will actually evaporate upon dispense and compression, so you avoid problems like that. But also it all goes into the proper dispense volumes and compression amount to determine how much squeeze out and how much running you get. Also, a big concern with that again goes to thermal grease selection is pump out during thermal cycling. You'll see that there are plenty of very reliable options out there, and you will see that the suppliers of those materials advertise low pump out.
Okay. The next question from Mike from Insilixa. What about the performance and lifetime in thermal cycling as it applies to TEC?
Abhishek.
So generally they are very robust devices. We do a lot of thermocycling testing, but some of the factors which can affect is the device size. So generally the larger the device is, the more warpage they can have, which can lead to defects. And then the other big question is the range over which you thermocycle or power cycle these devices. So the larger the range, the larger delta T you set up, and this will lead to a higher stress and can cause failures in devices. So generally, if you're operating between 30 and 40, you can have a very long time, very long lifetime for these devices.
Okay. This is my personal question, and I'm pretty interested in one of the statements you guys made, and that is the hybrid solution of active and passive cooling solutions. So have you guys considered, or are you working on maybe into the horizon of future product roadmap on chip integration? And let me supplement that with a specific application, and this would be the photonic ICs, where we see a lot of packaging or chip level integration, 2.5D, 3D. Can we apply TEC materials and localized cooling to take care of partial cooling of a sensitive component like a photonic component, with wavelength shifts and all?
Yeah, as without divulging too many details, we have actively looked at with some of those applications, and you're exactly right. There's a lot of ways to work at a component level on a circuit board where you have a sensitive component that might have issues that need to be addressed, whereas others may not. So that is definitely something that you can do, and you work it in with as we mentioned, whether it be a refrigerator or a circuit board design, you do have to know where you're bringing the heat to and where you're sending the heat, so we don't want to recirculate heat back into other parts of the board. So in general, what you need usually is a very thin device, and that's kind of one of the things that we specialize in. But in general, you don't have much room in those kind of applications. So ultra thin devices, but not competing with other like thin film technologies, but being able to fit form factors where you can fit into these small packages.
Okay, thank you. The next question from Kiran from Molex. How suitable are TECs in automotive applications?
Jesse, do you want to comment on?
Very suitable for automotive applications. They're very robust if properly installed, properly integrated into the system. They can be very effective at providing cooling or heating into automotive applications. Not typically to, say, cool an engine block, but perhaps a battery pack or a person. They're absolutely applicable.
Okay. Yeah, and this is Chris. Just to follow up on that real quickly, there are thermoelectrics, being used in automotive applications already, and then we see a lot of potential applications for autonomous vehicles, especially if cooling is needed for the multitude of sensors, like whether it be radar, LiDAR, infrared, whatever that might be used to, make sure there's no, oncoming traffic or pedestrians. So those are the kind of things that I think would be really interesting. I think are on the cusp of being vetted more fully.
Okay. The next question from Mike from Viasat. Can TECs be used in an environment where there's high vibration, large temperature swings, like over 100 degrees Celsius environment?
Well, the easy answer is yes, but I think as Abhishek mentioned earlier in his comment on the reliability of these thermoelectric devices, a lot of it comes into understanding those applications ahead of time and then building up the infrastructures either within the device or around the device to make sure they're reliable. I mean, as you can imagine, these are solid-state devices, they're semiconductor materials, so they're not like a metal block, which you can pound on. They do need to have considerations for vibrations, but we typically do vibrational testing and reliability of that nature on all the devices, especially that go into the datacom, telecom markets. They're very keen on, Telcordia type of reliability structure testing. So they definitely can. Now, large temperature swings, a lot of it depends. So the devices can be manufactured in such a way that they have a high tolerance for temperatures, and then they can also be manufactured in a way that they need to be, operated at less than 100 degrees C at all times. So that really comes down to the design of the device and very application-specific way of looking at how they're going to be used.
Okay. Next question from Mark for Radian. He's impressed with your Hex 2.0, thermal solution, but he's not so impressed with the price tag. So his question is, how do you compete when there are sub-$50 cooling solutions available in the market?
Yeah, so we're the technical guys.
Not
the price setters.
So you're not penciling for marketing yet, huh?
That's right. I'll be sure to pass on that feedback. No, in the end, here's what our value proposition with that product is. It is a high-end, high premium finish cooler, and it also provides unrivaled performance for its size. So in the end, that if you're doing a small form factor PC, that might be the highest performance cooler you can fit in that particular system.
Okay. One question from Steve Finizar. He's wanting to know that typically the manufacturers of TECs, they spec out a constant hot side temperature, which may not be constant or well known in advance. So how do you go about selecting? From a practical point of view, how do you go about selecting TECs when the hot side temperature is not well known?
Yeah, so the way we have really tackled those kinds of questions from customers is that we've kind of taken a different way of doing business at Phononic, and I can only speak for us, right, how we do business, is that we don't really have a catalog of parts that we say, here, give us an application, and we'll give you the closest thing that we have in the catalog. We really do a lot of application-specific designs because, as we've been kind of driving home in our overall presentation today, understanding the system and the environment that the tech will live in is as much a performance enhancer as the tech itself and the design you do. So if the customer doesn't know all the answers, that's fine, but we try to get as many answers as we can from the customer so that we can design something that gives them the best chance of success. So I think it really comes down to doing an application-specific design to get the maximum performance.
Okay. One last question. I know I'm pushing against the time limit. Gary from Affordable Brands, and he's asking, TECs will never be as efficient as compressor-type coolers. So he's wanting to know, how can we get to a state with TECs such that we can get Energy Star rating?
We don't have to get there. We are there. But I would challenge that thermoelectrics are not as efficient as a general statement of compressors. If you look at traditional high mass volume manufactured reciprocating compressors, thermoelectrics can operate in a refrigeration system at competitive efficiencies if implemented properly, and that can be seen in our products. However, there are thermoelectric solutions that are worse. There are vapor compression solutions that are better. So it's a kind of a hard can to wrap up with that. But in general, properly designed, they can be competitive with standard or average systems that are available today.
And just to make that point as clear as possible, there are Thermoelectric products, and again, not to be shamelessly plugging Phononic, but that reach and are Energy Star rated. So that is already, that's not something to reach for. It has already been accomplished.
Okay. With that, I think we have to close it. Thanks, guys. Phononics, everyone. It's been a great team presentation. Thanks to the audience. Very interesting question. I apologize we didn't get to all of the questions, but there will be a follow-up email. I think Phononics team will take some time to answer any unanswered questions. With respect to the Thermal Live event we are hosting today, it's been a great morning so far. We had a great day yesterday, so it's not too late to go register for any of the remaining sessions. And of course, we let you time travel. You can still register for yesterday and then download or view the presentations. We'll have a follow-up email regarding slides, but the video will be available within an hour or two of the session we're just concluding now. Thanks again. It was a very good, enjoyable, and rewarding session, so I learned a lot. And to all the attendees and the presenters and the Item Media team, have a great day, guys. See you. Bye.